Hello everyone! So today I'm going to be introducing you to a topic called chemical equilibrium. Just to give you a little bit of context, we usually would have talked about equilibrium when we were going through our solutions chapter, so talking about molarity, moles per liter, but things got kind of weirdly cut short because of what happened in March with us leaving right in the middle of kind of being about to speak about this. So we put a pause on equilibrium and moved into thermodynamics, but now we're going to go back to equilibrium because our next big unit is going to be on acids and bases, and you need to know what equilibrium is to kind of get the most out of that acid-base chapter. So this equilibrium is just kind of like a little intro right in the middle of thermo and acid-base. So for today's assignment, you are going to read through these 13 slides, listen to my screencast as you go. On the very last slide, there is a video that is a demo on making something called elephant toothpaste. It's a cool demo. It ties in a couple of things that you're going to learn about here, so that's a good thing to end with. And then when you feel all set and ready to go, there is a link to this exit ticket. I will also link this video in after I've made it. All right. So for equilibrium, we kind of need to change things up a little bit as we know them. So far, we've only worked with reactions that have a single-sided arrow. That arrow is always pointing to the right towards the products. And basically what this arrow is telling us is that we have some reactants, they're colliding, their particles are colliding, reacting to form products, and that reaction goes to completion so that when the reaction ends, there is no reactant left and all we have is product. Well, we're going to change that a little bit. That's where equilibrium comes in. So there is something called an equilibrium arrow, and that's what this is right there. It's two half arrows, and that's just the way that we kind of denote equilibrium. One facing to the right, one facing to the left, and basically what this is telling you is that this reaction is reversible. So my reactants can go to form product, and my product can go backwards to form reactants. And what we're specifically interested in is how fast my reactants form products and how fast my products form reactants. And there is a special rule when you're in equilibrium, which is that when you are in set equilibrium, the rate of the forward reaction, so the time it takes for these guys to become this product, is equal to the rate of the reverse reaction, the time it takes this product to become these reactants. And you know that you're looking, again, at an equilibrium expression when you see this double arrow. So what exactly do I mean by the rate of a chemical reaction? So the rate of a chemical reaction is a measure of the change in concentration of reactants or the change in concentration of products, again, they should be equal, over a certain amount of time. So recall also that concentration is measured in units of moles per liter, back to that solutions chapter, and we denote that as a big M. We refer to concentrations using the term molarity. And so from this graph down here, what you should be seeing is that the reactants are reacting to form products, and the products are deteriorating or dissociating to go backwards towards reactants, but the rates are just equal and opposite. And it's occurring over some set amount of time. So we're looking in that change in concentration over a given amount of time, and you should see that they're taking the same amount of time to change that same concentration. And that's how you know that you have an expression that's in equilibrium. So there are a couple of rules about equilibrium that you need to keep in mind as you kind of think about it and go through the slideshow. So first off, the concentrations of reactants and concentrations of products remain constant once your system has reached equilibrium. So if I have 1 mole of hydrogen gas at equilibrium, that's how much hydrogen gas I'm going to have. I'm not going to have any more, I'm not going to have any less. Regardless of the fact that concentrations are constant, particles are still rapidly moving when you reach equilibrium. So There is this misconception that once you hit equilibrium, everything just stops. That is not true. The particles are continuing to react to maintain that equilibrium. So they're still moving as fast and expending just as much energy as before they became equilibrated. I can't even pronounce that word. Equilibrated. And then lastly, moving on from that, the concentrations of the reactants do not need to equal the concentrations of the products at equilibrium. So equilibrium is looking at the rate at which reactants become products and vice versa, but reactant concentrations do not need to equal the product concentrations. So I could have 1 mole of hydrogen gas and 2 moles of water, and it would still be in equilibrium as long as the change between reactants and products, those rates are remaining the same. Okay, so now let's talk about what impacts the rate of a chemical reaction. So when considering a chemical reaction that is at equilibrium, we are especially interested in the rate of the forward reaction, so reactants becoming products, and the rate of the reverse reaction, products going backwards to reactants. Again, equilibrium, those rates should be the same. And there are 4 major factors that are going to impact how quickly a reaction occurs. Concentration of reactants, surface area, temperature, and the presence or absence of something called a catalyst, which we're going to kind of flesh out more in the next couple of slides. All right, so concentrations of reactants. First and foremost, raising the concentrations of reactants will cause a reaction to happen faster. Increased concentration equals increased reaction rate. And what you're going to notice is in all of these PowerPoint slides that we're going to talk through, all of these different factors impacting the rate of reaction, it all relates to molecular collisions. When molecules collide with one another, when a hydrogen collides with oxygen, the only way they're going to form water is if they collide. And so the more reactant particles there are due to an increased concentration, the more molecular collisions you can have, and therefore the more quickly you can form products. So here we have few molecules, there aren't as many collisions, so the rate of the reaction is low, whereas over here we have a whole bunch of molecules because we've increased the concentration, and so there are more collisions and the rate of the reaction is greater. Now, it's not just as easy as every time a particle collides, two reactant particle collides, they automatically form product. They actually have to collide in the proper orientation. So only a certain percentage of the particles that collide are actually going to react to form products. So here you can see, for example, that these guys are both in a proper orientation to become product, whereas these guys, this is an improper, ineffective collision. So this collision is not going to result in the formation of product. These particles are just going to bounce off one another. So more concentration means that you have a greater percentage or a greater probability that more particles are going to collide in the proper orientation to create product. Next up is surface area. So smaller particles actually have a greater surface area, and that's because the ratio of their interior volume is so small compared to the ratio of the volume that's taken up by the surface. So the greater surface area means greater availability for particle collisions, and more particle collisions, again, means faster reaction time. And so this is why powdered sugar, which has a smaller surface area than granulated sugar, would dissolve faster in water than granulated sugar would. And both of these guys are going to dissolve faster in water than a cubed sugar, which is going to have actually have the smallest surface area compared to interior volume. And so this guy is going to react the fastest. Third would be the temperature. As we know, when we increase the temperature, particles get excited, they get more energy. When they have more energy, they move around more quickly, and this quicker moving leads to more particle collisions and greater particle collisions. This is the this is the kind of pattern that we're noticing. Greater particle collisions means more reactions. So that's what this graph down here is telling us, that as the temperature increases, the rate of the reaction increases as well. And then, last but not least, is the catalyst. Catalyst, you've probably heard the term like something catalyzes something. Catalysts are substances whose jobs are to increase the rate of a chemical reaction. So if I add a catalyst to a reaction vessel, it's automatically going to increase the rate of a reaction. So under ordinary conditions, for example, hydrogen peroxide, H2O2, it's that thing that you can find very easily at CVS pharmacy. You put it on cuts, it's a disinfectant. On its own, it has a very long shelf life. It's not just going to decompose. But if you were to add a little potassium iodide to it, or you can also add yeast. Yeast works as well, and I'm not telling you to do this at home, but you could technically use hydrogen peroxide off of your shelf and yeast. Doesn't work as well as potassium iodide and strong hydrogen peroxide, but if you added the potassium iodide as a catalyst, you could actually make the reaction decompose in seconds. The potassium iodide causes the hydrogen peroxide to react and decompose more quickly. And this is actually the reaction behind elephant toothpaste. I highly suggest you watch this video. It's fun. We're not going to talk about how a catalyst works this year. You don't really need to know yet, but if you're really interested in why a catalyst works to increase the rate of a chemical reaction, join AP Chem and we'll talk all about it. All right, so that is today's content. Reminder, when you feel confident, go back and take the exit ticket. And then if you have any questions, feel free to reach out to me. Enjoy the day.